We have the pleasure of having with us today Professor Abdus Salam, who is one of the most distinguished scientists of our times. He is the director of International Center for Theoretical Physics in Trieste, which in fact he founded. He's been professor, continues to be a visiting professor at the Imperial College London. He's of course Nobel Laureate in physics, very well known in this part of the world. Professor Salam has been going around the country talking to scientists, academics, people interested in cultural activities, arguing with us about all kinds of things. And so we thought it'd be a good idea to get Professor Salam here and tell us a little bit about this tremendous excitement in physics which is happening these days. Professor Salam, you have yourself taken part in this big revolution which has occurred in physics and continues to occur. Why do you think physics is so exciting, and where is it going?
You see, physics has been transformed. Particle physics we are talking about has been transformed since, I should say, the middle of the 70s. We did not have, before the present excitement, any coherent set of theoretical ideas which would combine the various types of, which would give a direction to the subject. Fortunately, the work of the 70s, the work which started in fact in the 50s but culminated in the 60s in formulating a precise theory, and that theory was tested and found to be correct in the 70s, particularly towards the end of the 70s.
You're referring to electroweak? Yeah.
That gave a direction which is now embodied in what's called the standard model of particle physics. The standard model says that all matter is made up either of quarks, all the hadron, protons and neutrons are made up of quarks, or it's made up of leptons, electrons and neutrinos, or muons and their brothers, and so forth. So we enumerate 45 particles, still a large number, make them into 3 families of 15 each, which we say are the fundamental building blocks.
Well, you know, somebody who's not right into the middle of physics, he says, so what? So what's so great about this?
Well, what's so great about it is, I haven't finished yet, but can I just finish the standard model? The standard model then goes on to say that the 4 fundamental forces of nature are mediated by a set of 13 particles which go between, which are messengers of these forces. Now this totality of 45 plus 13 plus one more particle, the so-called Higgs, 14 particles, 59 altogether, makes up for all forces of nature whatsoever.
The forces being gravity, the force which keeps the nucleus together, nuclear forces, and the force of electric force, electromagnetic force, which is between charges.
And the fourth force is the one which... The weak nuclear force which is responsible for radioactivity.
That's right.
Now these 4 forces constitute all the forces we know of, all the 4 forces which from the beginning of the universe till today have determined what the universe looks like, what we are made of, what makes the earth what it is, a habitable place. So if this is called the theory of everything. If you have a theory of everything expressed in terms of quarks, leptons, and these fundamental 4 forces, I think it's a great triumph of human mind.
Theory of everything, but not necessarily a deterministic theory that everything was decided the first day.
No. That's a separate principle, the principle of quantum theory, which is overriding over the entire business. Now, this is the transformation which has occurred, as I said, in the 70s, towards the end particularly. 78 was the last experiment. which established the indirect nature of the correctness of our ideas. Then in 82 and 83, the particles which were missing in this whole scheme, the W and the Z particles, W plus, W minus, and the Z0, 3 particles, were actually made in the laboratory for the first time by Rubia and van der Meer, who got a Nobel Prize in 1984 for this discovery.
Even the masses of these particles were almost predicted, isn't it?
Well, that's the point. You see, our theory predicted the masses of these particles, and they looked precisely at those energies. The point was to have accelerators which should have those energies. No such accelerator existed.
That's right.
Before van der Meer and Rubia got to the business. Afterwards, when the accelerators were made, they looked precisely at the mass values which we had predicted and found them. And so everything was confirmed. Now, the question now arises, what happens next? And that is where we come in now. You may say, well, 45 to us is too large a number. Can we reduce it still further? Can we reduce from 4 forces we have reduced them to 3. Electroweak force is the force which is a combination of the weak nuclear force plus the electromagnetic force. The other 2 forces, the strong nuclear force and the gravitational force, stand outside this joining together. Why? That's the question.
So, how are things going?
Well, things are not going very well for 2 reasons. First of all, we need a still larger accelerator. Some are being made already. For example, at the Stanford Linear Accelerator Laboratory, they are making an accelerator which will make Zs very copiously. This will not find anything new, but it will make Zs a few times.
Incidentally, these are particles which have masses something like 70, 80 times the mass of the proton.
Like nuclei.
That's
They are very, very heavy
very particles.
To call them elementary particles is an act of faith, if you like. Now, what they will do with this Z part, this will come about in 87, towards the end of 87, this accelerator, the Stanford Linear Accelerator. It's end of 87.
The way particle physics or physics works now, is this true that theoretical ideas provide you many, many choices?
Correct.
And it's experiment which has to determine which is maybe the correct one and how to go further.
Correct. We would like to change it, of course. We would like to have everything predeterministic, like Einstein did with the relativity theory. But we are now faced with, at the moment, too big a task. We are trying to explain much more than Einstein did. We want to comprehend his theory as a simple, humble part of our theory.
But we haven't yet got a resonance with nature to say nature must really go this way rather than this way.
Well, that's what we would like to have. Well, that's the end of the theory. But may I just go on for a minute or to say what we are hoping to achieve in the chronological order? You see, as I said, we haven't got the accelerators, and these 2 accelerators, one at Geneva, which is 27 kilometers in circumference, 27 kilometers of tunnel, which you were explaining quite rightly to the Prime Minister this morning. That tunnel is being completed, and it will come, as you said quite rightly, from the tunneling from 2 sides, and it will come together to within 1 millimeter. That's being done with laser accelerators, with laser things. Now, that tunnel is being constructed under the mountains of Jura, and that will be ready in 1989, from 3 years from now.
You need a large diameter tunnel because these high energy particles have to be bent around to come back, and magnetic fields essentially.
But the trouble is that the electrons, if they are very fast, emit radiation so much that you will need to pump so much energy into it that Geneva does not have. So the larger the tunnel, the better.
Because once they bend at a smaller rate, they radiate less.
Exactly. So these accelerators will be ready in the 1990s and will answer questions about the correctness of our theory to 1/10 of 1% accuracy rather than 1% accuracy. The hope is there will be some small deviations.
Discrepancy. That's where the information is. Right?
That's where the information lies. Those small discrepancies will then point the way towards newer particles, which we have missed out in this count, and newer types of thinking will arise. Newer choices will be. We've tabulated the choices possible. I was showing this graph yesterday of the possible choices, 1, 2, 3, 4. Which choice nature will take at the moment, we do not know. We can only make guesses and so on. Then after this is done, then there is the other side of the joining together. This is still electroweak.
Yes.
Then there's the other side of joining of the strong nuclear force and the gravitational force with the electroweak.
That's right.
The strong nuclear force is a very terrible thing to join together. The only experimental work is the proton decay,
yes,
which you are carrying experiments in Bangalore at the Kolar.
Yes.
Unfortunately, those experiments are getting nowhere. They are terribly difficult to perform because of the background of neutrinos. A neutrino can go right through the Earth, yes, without being at all reflected.
These are experiments which are underground to filter out the cosmic rays, but neutrinos still get in. Neutrinos still get in, and they make interactions.
And this is impossible to obviate them. So either you go to the moon and do the experiments there, where the neutrino flux is 1/100th of what it is on Earth, or you just make the detectors very, very large and hope for the best.
Or make them much more intelligent. Supposing you could measure the energy very accurately, that it is a proton mass and no more or no less.
Could be. But anyhow, these experiments are not getting anywhere, so that's one of our sorrows. Then there is the possibility of final unification, that's of gravity, together with these forces, these three forces.
Of course, you haven't explained to our listeners how is proton decay connected with unification.
Well, that's, you see, if the proton is the same particle as the lepton,
yes,
the lepton being the electron.
That's right.
You see, previously, in the electroweak theory, the protons and the electrons are treated separately. If they are the same particle, then one can transform into the other.
Yeah.
And we can tell what the age of this transformation should be. It should be greater than 10 to the 30 years.
Yes.
Since the life of the universe is only 10 to the 10 years,
yes,
that of course doesn't affect the fact that we exist and so on. However, it's a very important concept for which we would not like to lose, because this explains many things. Why, for example, we don't have antiproton stars and
that's right,
things like that.
Here, really, the kind of physics one is interested in is begins to impact the whole of cosmology, or vice versa.
That's right. That's right.
One could even do cosmological studies.
Yesterday I was saying to my audience in Bangalore that physics used to be a troika, theory, experiment, and accelerators. Now it's a quintica. Why? Because astronomy, astrophysics, has joined particle physics in making one single subject. We can,
that's right,
all the early universe from 10 to the minus 43 seconds
right,
up to 10 to the minus 12 seconds.
That's right.
Is comprehended by particle
physics.
The fifth element of this, the new element, is the mathematics. It's amazing. We did not have to care. Res Yost in the 50s used to say, all the mathematics a physicist needs is a rudimentary knowledge of Greek and Latin alphabet so that he can put indices onto his equation. That's no longer true. We really now need the most modern mathematics.
Yes.
Algebraic topology, Riemann surfaces, things of that variety. Very, very modern mathematics.
Yes.
Top grade mathematics. And that is a very new thing. It's happened in the last 5 years. This whole development has taken place in the last. So, going back to my unification stages, the last one is the gravitational unification. And that is the most difficult. We did not have any real good ideas till last year, till 84, till the end of 84.
What happened in 84?
And in the end of 84, two men, one an Englishman Green and one American Schwartz, they discovered that there is two theories only, which they call the string quantum theories, the string theories, in which you do not talk of single particles, but whole strings which are created and annihilated. And those strings, these strings are nothing very mysterious. They are, suppose I have a quark here and an antiquark here, then the force between them is, we think of it as something which is momentarily passing across.
Yes.
But these people assert, no, it's like a string tying the two together. And then you start worrying about the oscillations of that string. And the amazing thing is that those oscillations, the lowest oscillation is gravity. It's incredible. It's incredible.
The string has all possible forces in it.
No, let's tie a string between a quark and an antiquark. Actually, it's slightly more complicated. You have to, don't think of a quark and an antiquark, think of it as a round string just by itself. And endow each point with a fraction of a charge, charge density. Right. Now take the string. Assume that it's a solid object. Let it oscillate. It will have all manner of oscillations. Take the lowest possible oscillation, zero frequency as we say.
You have to give certain properties to the string.
So the tension is the only property which you need to give it. Only one parameter, tension. That tension, in the limit that tension becomes infinite, or the inverse of the tension goes to zero, you discover that this string represents the force of gravity. It's a difficult concept to get into. And we don't know the reason. That's the funny thing of it. Nobody knows the reason why this is happening, why gravity of all forces.
But where do the mediating particles and Higgs bosons and all kinds of things come in to make it so?
Well, I'm coming to that in a minute. So, now this string has to live. It cannot live in less than 10 dimensions. That's another funny thing. If you wrote its equations of motion in 4 dimensions, they'll be inconsistent. So it's 10-dimensional gravity we are talking about. 10-dimensional gravity is the same thing, if you like, as 4-dimensional gravity plus strong, weak, electroweak forces and so on. So this is the connection which you make.
I see.
And then all the quarks and stuff comes out once you do this. It's the most exotic theory. Now, we have hopes from this theory that this will prove to be finite. That hope, if it's not fulfilled, we shall all leave it. So in another year, you may find nobody wants to talk about it. Or in another year, you may find that this is the final candidate, or say at the moment the final candidate for the theory of everything. So this is the sort of stage you reach. Now you'll ask, how will you test this theory? What distinguishes this theory, apart from predicting the stuff which you know already, 45 particles plus 13 messengers of force and so on. What else does it do? Unfortunately, we do not know quite well how to get this theory down to 4 dimensions and get other predictions. One prediction which was made in the beginning of January, this last year, 85, was that this will predict another Z0, one more Z0. Now that prediction has become a bit doubtful. It's still there, but it's not unique. There may not be a Z0. So at the moment, if you ask me what is the new characteristics which you will measure from this theory, I cannot tell you.
I see. But it is not, you said it should be finite, but it doesn't predict things, but if new things are found, it could incorporate other things which are found.
At the moment, it's incorporating everything which you know about physics.
And no more. We don't know.
We don't know. You see, as I said, there was the prediction of one thing more.
Yes.
But that's no longer compelling. Somebody has found another solution of the equations of motion in which those predictions are not compelling anymore. So we really have still to learn how to deal with. This is a type of mathematics which certainly was invented by Riemann. Then Teichmüller is a German Nazi soldier who did lots of work on it. During the war he was killed. Then after Tycho Muller, it's been worked on by other mathematicians. And now we are all reading the mathematics books and finding enormous gaps. For example, the fourth loop in the Tycho space is not yet tabulated. So we have to learn mathematics. At the moment, we have to invent the mathematics. The physicists have to invent it, or the mathematicians have to do it for them. And so it will take us a fairly long. For example, this young man, Witten, who is the most bright man at the moment in this subject, he's about 31 or so. He says, this subject will occupy us for the next 50 years. That's his prediction. Now, we should listen very carefully to him, because he is the most profound man at the moment who writes on this subject. And so, and many Indians, that's what I was saying. That's what I was saying. These Indian young men, both here as well as in the US, are fully in the thing, at the highest reaches of the subject. So you should be very glad about that.
But what is there something new epistemologically which one is learning?
Well, epistemologically, it's all upset everything you knew about theories. For example, as I said, Einstein's theory was based on curved space-time. You remember, Einstein said there's no gravitational force as such. It's all curvature of space and time. Why is the curvature coming out of string theories? Why? We don't know. See, it's the funny thing, as I said to you, you start the theory in 10 flat space-time dimensions, and out comes a curvature. It's a funny thing.
Is it? It is understood well enough. It's not mysterious.
It's not mysterious in the sense that we do it every day. But it's mysterious in the sense that we do not know why it's happening. So in that sense, all symmetries are in the thing, but we don't know why. We don't know why. We could not have predicted unless we had solved the equations. And this is a new situation for us, very unpleasant situation. So we have to change that, we have to do higher order calculations, we have to see that the thing works properly and so on. And so it's a fascinating stage. Any young man worth the salt, he should be, if he is minded that way, and he is good in mathematics and so on, he should be encouraged to keep at it for the next 10 years or so. And if it doesn't make any good, then he should go away.
It is not merely just an elegant description of
not at all. We don't understand it.
Elegant economic description of, but it is deeper than
something
that.
Totally new, which happens to give at the end of the day the same things we've been doing before. But why? We don't know. It's a very, very strange. Of course, it contains much more stuff, which I don't really know. Many more things. But those we don't care about. We at the moment are worrying about the zero frequency things, like the graviton and like the gluon or like the W and the Z and so on, the normal W and Z and the photon. They all come out of the damn thing.
The masses and properties.
No, not yet the masses. But the properties come out. We know how to get, we shouldn't say we know, but we have the possibility perhaps one day of getting the masses and so on. This is a long, long way off yet to get everything out. But the hope is that everything will come out. And so far, the one loop calculations have proved to be finite. And that's the funny thing. So it's a really a totally new world which has opened up for the theorists. For the experimentalists, they couldn't care less. No, they're right not to care about it, because if we keep changing our predictions, they can't take any serious notice.
But you know, experimentalists, poor experimentalists, what they get to do depends so much on the prestige of what a theorist is saying.
No.
Otherwise they don't get funded these days.
That's a great pity. But you see, they don't get funded anyway now. I mean, take the old theories, which we are sure about, the theories of supersymmetry, so-called, and so on, for which we need an SSC, so-called, a big accelerator of 20 TeV plus 22 EV.
Supersynchrotron or something.
Supersynchrotron, yes. Now that is not being funded in the US, for example. And so it's a very, very serious situation at the moment.
What can one do in terms of astronomy to do experiments which would be of specific importance to particle physics?
Well, one of the 3 or 4 neutrinos, for example, from the helium abundance in the universe.
Helium being about a quarter of hydrogen.
Helium being a quarter of the universe is...
And supposed to have been made all in the early universe.
That's right, the very early universe. Now, the number of neutrinos depends upon that.
Yeah.
This is 3 or 4. Now, experiments found, first time the experiments in the laboratory confirmed something from cosmology, that the number of neutrinos is most likely to be 5.4 plus minus 1.
Sorry? 5.4 plus minus 1?
Yes.
Oh, this is just from the close-up, from the acceleration parameter and so on.
That's right. That's right.
Otherwise, the total amount of...
No. This is the laboratory experiments on the width of the Z0.
I see.
Which is connected to the neutrino.
All right. Okay.
Now, the 5.4 is, well, it's near a 6 or 4 or something. This is a larger number than 3, for example. Now, they re-examined, this is John Ellis and others, they re-examined the data on helium-4 and helium-3, and they find that in fact, according to the new data, up to 6 neutrinos are allowed.
I see.
So that's one thing which will now form a more detailed measurement of the helium abundance, more accurate helium-4 and helium-3 abundance, will be called for.
Yeah.
Which the astronomers could do.
Well, the trouble is where you look, it varies a bit and so on and so forth.
Well, this is one point. The other point I was mentioning again at Bangalore yesterday was the existence of Cygnus X3.
Yes.
This object is giving out in the pulses of X-rays, and probably it's...
High energy gamma rays also.
That's high energy gamma rays also. And it's producing muons at the end in the atmosphere. 4.8 hours cycle. It's got the luminosity of 100,000 suns.
Mm.
So it's an incredible accelerator, if you like.
Yeah.
And 10 to the 5 TeV, 10 to the 5...
1,000 GeV.
1,000 GeV. It's an incredible energy with which it's pouring out lots of material. Now, if there could be other such signals, they could be extremely valuable, extremely valuable. So if you really wish to look for astrophysical things.
What about things like neutrino mass?
That's another example of, that will provide another very important input among the parameters, which will be very useful for our eventual theories. Another place to look for where astronomy can provide stuff is invisible mass.
Yes.
One believes, as you know, that the mass is probably 1/10. The mass now seen is probably 1/10 of what it is.
Some people say that maybe it's in neutrinos.
Maybe it's neutrinos, maybe it's gravitinos, maybe it's photinos, maybe it's all sorts of speculations are made. The precise nature of missing mass, if there is some, would be extraordinarily welcome for our theories. So astronomy can do a lot for particle physics. Another thing on which astronomy could cast a little light is the variation in the fine structure constant with time and the variation in the gravitational constant with time.
I know, but what accuracy do we need?
Well, already we know that it's not varying to 10 to the minus 13, 1 part in 10 to the minus 13. We need better accuracies than that. We need something like 10 to the minus 17 or 16 or something.
1 part in 10 to the minus 13.
For G dot or G, for gravitational constant or G, G dot or G.
You know it from astronomical evidence, right? Astronomical and ecological and also geological
arguments, yes.
Yeah.
Yes. So if you could do better on that, that would be another good parameter.
I don't know how astronomy would do much better than that. Maybe. We measure up to redshifts, what, 5, 10? It's difficult. Redshift 3, 4, 5, 1 is gone. But
Yes. But anyhow, these are various things on which astrophysics and astronomy, early cosmology could help us. But the thing, as I said, was the fascinating vitality of the subject, incredible.
I think the magnificent part is one is here talking of range of times 10 to the minus 43 to 10 to the 30 years.
10 to the 43 seconds.
Minus second to 10 to the 30 years.
Seconds.
Yes.
Yes, that's right. 60 orders of magnitude.
Yes.
Yes.
And forces which...
That's right.
And then everything in the middle is just a
everything in the middle is just a consequence.
Is it the only possible world we have, or
that's another,
the best
that's
possible world we have?
That's another subject on which we don't know, and we would like to know much more. This is the theories of the inflationary universe,
Yes.
and how many universes there are, and if there are other universes, how do you comprehend them at all
That's
in
right.
the schemes and
That's
so
right.
on. Then there's the theory of shadow matter. You may be... There is two parts of this equation from the strings. Well, I'll just mention the technical names without telling you about them. E8 cross E8 is the sort of group on which we work on. One E8 controls all of life here. The other E8 is only apprehended, it's called the shadow world, it's only apprehended through gravitational forces. So for all you know, there may be a gravitation. There are second E8's mountain here. We are living inside a mountain. Whose only presence is through.
You know, once talking with my colleague and friend Kaushik, discussing, we were talking about neutrino mass, okay?
Yes.
Missing mass and neutrino mass.
Yes.
So if it's turned out that neutrinos do have a mass, a few electron volts, then essentially the gravitational structure
Yes.
and all the potential values and so on is really determined by neutrinos, and the visible universe are just test objects to see how it's distributed.
That's right.
So we are just doing experiments for somebody to find out how the rest of it is doing.
Yes, yes. Now, it's an incredible situation in particle physics, and the great pity is that just now the temper of the societies in the West particularly is turning away from big science, just now. When we have finally broken the code and we have... You see, we are in a totally different phase than when I started physics. When I started physics, there was no coherence at all. There was islands here and island here and islands there, and there was no coherence about the subject. Now we have a coherence. There's a beautiful theory whose parts have to be found from experiment at the present time.
Yeah, but somehow this is the tragedy of modern times. I believe a very deep tragedy.
Yes.
That possibly science has been so successful in applications, in making technology, that we are beginning to forget what science means for being human. You know, in terms of this, I think it's our destiny to be involved in this, if otherwise we're not human.
Yes, but you see,
itself
people
implies-
say, and other scientists in fact say, at what cost? You see, this
I
is
know, but the cost. I mean, you have mentioned, and I have mentioned, the point is, what are your passions?
Exactly.
For following the agendas of yesterday and day before day, what are we spending on things which are not going to take us very far?
That's right.
And so, being involved in science is a different matter.
That's right.
And I personally believe that being involved this way has implications which are much larger. Whether it's appreciation of beauty, culture, even I would say objectification of values.
That's right.
I think they are all part of it.
Well, this is where it's so painful to be on the defensive, honestly, to be able to justify why you should do these experiments and so on. It's a terrible tragedy.
But anyway, it's fun to do it.
Oh, well, certainly it's fun for me to do it.
Yes.
I think I will probably survive till the present set of accelerators is still
Yes.
busy.
Yeah.
But what will happen to our children? That's what worries me. Because we
Of
must
course,
leave them a legacy
Yeah.
of already accepted projects, just as our forefathers did that to us.
Okay.
And that's what's passion, that's the passion which I have.
And thank you, Professor Salam. Thank you very much.